Hi everyone, this is Arezoo and I'm going to present on the behalf of our group on integrated path planning and tracking control for marine current turbine operating in an uncertain oceanic environment. At first, I'll give you the background and motivation behind the work. But the main question here is why renewable energy? These are important resources for us to reduce the reliance on the fossil fuels and also improve the blue economy. There are different types of energy resources in marine environments, such as wave energy, tidal energy, ocean current, river current, and ocean thermal. We have different types of technologies to harness this power, and these are shown in this figure. So among them, we focus on the ocean current and marine current turbine system. There are different applications for these technologies, such as water desalination and powering disaster area to benefit the blue economy. But the main challenge for this system are high cost in design, operation, and maintenance. So we need some mature research in this area. Okay, specifically for the ocean current energy, I should mention that there is a high potential for power generation from ocean, such as 44 gigawatt from the Gulf Stream current and 5 gigawatt from the Florida current. Here, at Florida Atlantic University, we focus on the marine current turbine system and perform some on-water testing. I should mention that the ocean power is depth dependent and the highest values are located near the sea surface. So we need some mature technologies to harness this power and navigate the system through the water column, such as lifting surface control and buoyancy control system. And we specifically focus on the buoyancy control one. But in the literature, we lack a kind of integrated path planning and tracking framework for the MCT system to formulate the path control for this system. Okay, at first I discussed the modeling of the buoyancy control MCT and the oceanic environment. So we designed a 700 kilowatt MCT system, which is initially designed to operate in the Gulf Stream of Florida's East Coast. This system is designed for the real environment, and we use some sample systems such as MCT designed by HI company. And this system includes two variable buoyancy tanks, which is located in one variable buoyancy chamber, also the main body, the variable pitch rotor, and the mooring cable, which is used to attach the system to the seafloor. Then we should identify the main states for the system. We have 14 states for this system, including linear body position, Euler angle of the body, linear velocity of the body, and angular velocity of the body. Two remaining states are related to the variable pitch rotor, including rotation angle of the rotor blade and angular velocity of the rotor blade. We also have three actuators for controlling this system, including variable buoyancy fractions and electromechanical torque. I should mention that this system, the movement of this system is initially controlled in the vertical movement, and the field fractions are mainly responsible for this. Okay, then we want to formulate and write the equations of motion for this system. This system is modeled with 7 degrees of freedom, including 6 degrees of freedom related to the motion of the main body, and the last degree of freedom, which is related to the rotor's rotation about the x-axis. So then we want to identify the coordinate frames for this system. We have 5 different coordinate frames for this system, including inertial coordinate frame, body fixed coordinate frame, momentum mesh coordinate frame, shaft coordinate frame, and rotor blade coordinate frame. So after finalizing this, we should write and formulate the forces and moments acting on the system. We have 5 different forces for this system, including gravitational and buoyancy force, body force, force acting on the variable buoyancy, rotor force, and cable force. We have the similar condition for the moments acting on the system. So we can now have the complete equations of motion for this system. After completing the modeling and designing the system, we now want to assess the performance of our system in different conditions before putting this in the real environment and design the real turbine system. We just addressed this in our previous paper and simulate several conditions. The first case is related to the homogeneous flow and shear flow, which is some simplistic oceanic environment, and we show the successful operation of the system in this condition. The second case is related to some faulty conditions, including rotor stop and pitch imbalance, and we specifically show the pitch imbalance result here. And this system can successfully operate in faulty condition. And also the last case, which is related to the realistic ocean flow, where we use some real recorded data from the Gulf Stream and simulate both normal and hurricane condition, and our system can successfully operate in different conditions. Okay, then we want to model the oceanic environment. We know we have some spatio-temporal uncertainties in the current flow due to some turbulence, waves, and lower frequency flow structures. So we use some real recorded data, which are gathered by acoustic Doppler current profiler or ADCP from the Gulf Stream. And then we just pick several methods and just compare the results together. We see that the Gaussian process model shows the best performance. So this method uses a kind of a bunch of recorded data at discrete operating depths and different time slots. And then we can model the Gaussian process model with having the mean and covariance calculated based on the data. Okay. Then I want to show you the integrated path planning and tracking control, which is proposed for the MCT system. We have a kind of bi-level framework for the MCT system, where the upper level is related to the path planning and the lower level is related to the path tracking. Okay, the upper level, which is related to the path planning, wants to maximize the harness power from the system. This objective function is formulated according to the constraints on the spatio-temporal uncertainties in the oceanic environment and some inequality and equality constraints on the MCT system. We also have some constraints on the MPC-based path tracking controller, which wants to minimize the tracking error and solve the optimization problem according to the linear model and the MCT movement and actuator and also state constraints. The third block is related to the Gaussian process modeling to model the oceanic environment, and the last block is related to the linear model of the MCT. So since we have the reinforcement learning algorithm for the path planning, we should have a kind of offline training phase to train the network. So after the training the network, we can find the optimal path and find the optimal network, which is used in the online phase. We use some historical recorded data from the Gulf Stream to train this network. Then, after completing the training, we can go through the real-time application or online phase. In the online phase, we use the train network to find the optimal path. Then we have the MPC-based path tracking controller, which is responsible for finding the optimal actuators for the MCT system based on the optimal path from the path planner and also the linear model of the system. Okay. I now want to discuss the path planning problem. The path planning problem is proposed based on a spatio-temporal optimization problem, which wants to maximize the harness power from the system and also consider the uncertain oceanic environment. In this problem, the MCT is as an autonomous underwater vehicle with a primary role of energy generation. So we should find and calculate the harness power from the system. We want to approximate a linear model for the harness power from the systems to avoid any computational complexity. We're using the dynamic modeling of the system. So we approximate the linear model for the vertical movement and net harness of the power from the system in the path planning using some similar policy. The vertical movement is modeled with any changes in the field fractions, where the changes in the field fractions are modeled with the changes in the ocean current velocity or any changes in the operating depths. We also have the net harness power, which is modeled with three terms. The first term is related to the generated power from the MCT system, which is due to the ocean current velocity. The second term is related to the power consumption to hold the operating depths, and the last term is related to the power consumption to change the operating depths. We also justify this linear equation with the nonlinear model and show its approximation. Then we use the reinforcement learning algorithm and propose this approach to formulate and solve the path planning problem. Just as a quick background to the reinforcement learning algorithm, this problem is formulated as a Markov decision process. In this problem, MCT is treated as an autonomous agent which observes the current states, takes some action, which results in a reward and also a state change. So this is the main idea behind the reinforcement algorithm. So to recast the path planning problem into reinforcement learning structure, we should define the state space, action space, and also reward function. Specifically for the path planning problem, the state space is defined based on the current operating depths of the system and ocean current velocity at discrete operating depths. We also have the actions, which is defined based on the set of discrete operating depths which can be placed by the MCT. The reward function is defined based on the positive constant value which is given to the system if the net harness power from the system is increasing. We picked the deep Q network approach among the reinforcement learning algorithm to solve this problem. And then for just balance the exploration versus exploitation in the training phase, we use a kind of adaptive epsilon greedy policy to train the network in finding the optimal actions. Okay, then I want to discuss the path tracking problem for the MCT system. This problem is formulated based on model predictive control. The objective function is defined to minimize the distance between the MCT current path and the optimal path, which is commanded by the path planner. Then we have the second term, which is related to minimizing the control input changes. So with minimum changes in the actuators or control input, we want to follow the optimal path. This objective function is defined based on the constraints on the control inputs, including field fractions and electromechanical torque, and also constrained on the slow rate of changes in the field fractions. Okay, now I want to show you the simulation results. We simulate this integrated framework for different cases. Among them, I show you the first simulation, which is related to the optimal path with low depth changes, and also optimal path which high depths, which show high depth changes. So these two cases are shown in this figure. For these two optimal paths, we can see that the path tracking controller can successfully follow these two optimal paths. I also show you some states, including Euler angle of the system and control inputs of the system. We can see from the figure that this system can successfully operate, and the states and control input changes are successful in following the optimal path, and these control inputs do not violate any limit. So we show that our system can follow different trajectories by path tracking controller. Okay, now I want to conclude the presentation and discuss the future work. Okay, in this presentation, I present an integrated framework for the path planning and tracking for the buoyancy controlled MCT system. In the path planning level, we maximize the net harness power from this system, and we use the deep Q network approach to solve this problem in a discrete oceanic environment. Then in the path tracking level, we want to minimize the tracking error, and we use the model predictive control approach to formulate and solve this problem. We consider that our proposed framework can be extended to other energy harvesting autonomous vehicles, such as wave energy converters or airborne wind energy system. We have some ongoing works in our lab, including presenting an integrated path planning and tracking framework, which also consider the collision avoidance and only formulated by deep reinforcement learning algorithm. And we use the proximal policy optimization for solving both path planner and path tracking controller, and it considers the problem in continuous environment. We also present a control co-design framework for the MCT to couple the physical design and path control together and just find the optimal MCT system. I highly appreciate your attention, and a list of related publications from our group is shown in this slide. Thank you.